Alrighty, so we're going to start section 7.3, trig substitution. And you'll notice a pattern that, in every section that we do, besides the application section, we start looking at, certain integrals we weren't able to do and coming up with ways to do them now. So let's take a look at the integral. So let's start with the integral square root of a squared minus x squared dx. And you can take a look at this and you can try and do, all the different things that we've learned so far: integration by parts, use substitution, try and find an antiderivative. None of these are going to work. So let's take a look at the integrand though. So the integrand is a squared minus x squared. So we want to try and put this in a form that, allows us to integrate this thing a little more easily. So the motivation behind this is if you let x equal a sine theta, I can plug this in. It's going to be a squared minus a sine theta squared. Which is square root of a squared minus a squared sine squared theta. I can factor out that a there, that a squared. And when I do that, when I factor it out, I can take the square root of it. I'm going to get a times the square root of 1 minus sine squared theta. And now I remember back to my trigonometry, and I know sine squared theta plus cosine squared theta is equal to 1. So 1 minus sine squared theta, if I subtract the sine squared theta, it's going to be cosine squared theta. This then is equal to a times the square root of cosine squared theta, which is a times the absolute value of cosine theta. And depending on the region that we're looking at, this might be positive or negative. We want it to be if we can get rid of the absolute values, that's good. But the point is this is much easier to integrate than that was. The square root of a squared minus x squared. So what we're going to do is I'm going to pull up the table of trigonometric substitutions. If you look at page, go back to the black pen. It's in page 486. You'll see this table of, let's zoom. You'll see this table of trigonometric substitutions. So what we're going to do is, you can use this to help yourself, but you should really just kind of be familiar with the process and be familiar with what to look out for. So the idea is, if I have, let me get some of my drawing tools up. So if I have this expression, a squared minus x squared, square root, I'm going to do the substitution x is equal to a sine theta. And we're going to restrict theta to be between negative pi over 2 to pi over 2. The identity we want to use to simplify the square root then is that identity. 1 minus sine squared is equal to cosine squared theta. Another form of this would be square root of a squared plus x squared. For this one, we're going to let x equal to a tan theta, take the same restriction. And the reason we do x is equal to a tan theta is because 1 plus tan squared theta will be secant squared theta. The last one we have in the table is square root of x squared minus a squared. X is going to be a secant theta. And then depending on, what you want to be positive or negative or what your bounds of integration are, these are the restrictions. And your identity will be secant squared minus 1 is equal to tan squared, which is the same thing as the one above it, just rearranged. So I'm not going to write this down because it takes too much time, but I'm going to reference it as I do some problems. So you might want to keep it around or keep your book open. So I'm going to jump into my first example of how to do this. So we have example 1. There are going to be some parts that don't make sense the first time around. We're going to have to do them every time we do this, though. So they should start making sense at some point. once you've seen it enough. So example 1 is to evaluate the integral of the square root 9 minus x squared over x squared dx. And so the point is, I have this square root thing that I didn't know how to deal with before. But now that we have that chart, we know how to deal with it. I'm going to start doing my scratch work in blue here. So what I'm going to do first is I'm going to do my trig substitution. Let me try to make my drawings a little bit. Yeah. We're going to do x is equal to, and then, okay, so what is a in this case? So remember, if you look back at the table, so I can pull it up real quick. I won't do this every time. So the form we're looking for is a squared minus x squared. So I have to, it's not 9, I'm not going to write 9 for my a. I need it so that when I square it, I get 9. So that's going to be 3 sine theta. And the point is, I'm going to plug this in for x squared. That 3 is going to become a 9, and that's what I'm looking for. Whatever, I'm wanting whatever this is in front of the sine theta to become, that 9 in the integrand. So I take x equal to 3 sine theta. And now because I'm integrating, I can't put this in terms of dx anymore, so I have to do it in terms of d theta. I'm supposed to be doing scratch work in blue. So if I find the differentials here, I'm going to get dx is equal to 3 cosine theta d theta. Now I'm going to plug this into my integral. So I have the integral square root of 9 minus x squared over x squared dx. This is going to be equal to the integral square root of 9. X squared is going to be 9 sine squared theta divided by x squared again is 9 sine squared theta. And then I'm going to replace dx. Dx is 3 cosine theta d theta. All right, so this doesn't look like it helped me much because now I have all these trig functions running around. But let's go ahead and do our simplifications. I'm going to pull a 9 out of the square root up top. I'm going to pull a 9 out of here. When I do that, I have to take the square root of it. So I'm going to get 3 square root of 1 minus sine squared theta divided by 9 sine squared theta, 3 cosine theta d theta. 3 times 3 is 9, so the 3 and the 9 cancel each other. So what I'm left with then is, and then again, so I have a 1 minus sine squared theta. I know that 1 minus sine squared theta is cosine squared theta. So I'm going to use that. So I'm going to get the square root of cosine squared theta divided by sine squared theta cosine theta d theta. I'm just going to keep simplifying. So the integral from negative pi over 2 to pi over 2, cosine's positive. So I don't have to worry about the absolute value. This is just cosine theta divided by sine squared theta cosine theta d theta. And we just keep going. The integral cosine squared theta over sine squared theta d theta. We have to put this in a form we know how to integrate. So let's try and write this. This is going to be cosine squared divided by sine squared is cotangent squared. Now, it's harder to integrate things with quotients, so division in it. So we're going to write that as cotan squared. We don't know what that is off the top of our heads, but we have an identity. So with this identity, sine squared theta plus cosine squared theta is equal to 1. We can get all the other identities that we need. So if I divide everything by sine squared theta, I'm going to get 1 plus cotangent squared theta is equal to 1 over sine squared is cosecant squared. So cotangent squared then is cosecant squared theta minus 1. That's going to help us y, and that's going to help us, and we'll see why in a second. This is going to be cosecant squared minus 1 d theta. So if you look into your table of integrals, you'll see that this one appears there because it's the derivative of a simple function. So this is going to be the integral of cosecant squared theta, split up the integral, minus the integral d theta. So you look in your table, you remember that the derivative of cotangent is cosecant squared, negative cosecant squared. So this is going to be minus cotangent theta minus theta plus a constant. So let me just take a second. This came from there, this went there, this went there, and the integration constant came from integrating. But we have a problem here. So you might stop here and think, okay, I have this thing, it has a plus c, I'm finished. We are not. So if we look at the original problem, everything was in terms of x. So we have to go back and put everything in terms of x. And this is going to be a little harder than what u substitution was, just because it's, before you picked u to be something in terms of x. Now we're setting x equal to something, so we're going to have to find inverse functions. So you remember that we said x equal to 3 sine theta. I can solve this for theta. I get theta is equal to arc sine of x over 3. So I'm going to plug this into my answer that I got. So I'm going to get minus cotangent theta. Sorry, cotangent. Theta is the arc sine of x over 3 minus arc sine of x over 3 plus a constant. All right, so you might think we're done here, and you are wrong in this case. So this second one I'm finished with. I can't simplify that at all. This first one can be greatly simplified. If I don't have to do things in terms of these trig functions, Vark trig functions, I'm going to be in a better position. So let's talk about how to do this. It's going to be the same exact thing every time we do this. So first thing that you should remember is that, if I do the arc sine of something. So remember, arc sine and sine are inverse functions. So think about what sine does. Sine takes in an angle. So you take the sine of an angle and it gives you a ratio. It gives you the opposite over the hypotenuse, SOHCAHTOA. So that means then the arc sine, what you plug into that is you plug in a ratio and you're going to get an angle out. Sorry, they're apparently doing fireworks for whatever holiday weekend this is. And I'm terrified my dog is about to start losing his mind. If he does, I apologize. I'll try and finish this up before he does. Okay, so anyway, so arc sine takes in a ratio, spits out an angle. So what you should remember is this arc sine of x over 3, this is just an angle. So if I draw a triangle using the arc sine of x over 3 as my angle, so let's call this angle the arc sine of x over 3. I want to start filling out these sides. 2 of them I can do. So we know that arc sine and sine are inverse functions. If I look at the sine of the arc sine of x over 3, this is just going to be x over 3. So that means the sine of this angle here, the sine of the arc sine of x over 3 needs to be x over 3. Sine is opposite over hypotenuse, so if I just set the opposite side to be x, the hypotenuse to be 3, then if I take the sine of this angle, I'm going to get x over 3. Let that sink in for a second. And, depending on, if this were arc cosine or arc tan, that's going to be how you do it. If it were arc cosine, cosine is adjacent over the hypotenuse. So that would tell you what the adjacent and the hypotenuse hypotenuse side r. So if this were arc cosine, the adjacent side would be x, the hypotenuse would be x over 3. We'll see some more examples of this. Okay, so with that, I can use the fact that, if I call this, I'm going to just label it y real quick. I'm going to erase it in 2 seconds. I know that x squared plus y squared should be equal to 3 squared, which is 9. That tells me y is equal to the square root of 9 minus x squared. So this side then is, this side is the square root of 9 minus x squared. Now, why did I do all this? I did all this because I want to put, my answer in terms of these terms here if I can. So what I'm going to do now is if I want to take the cotangent of the arc sine of x over 3. So if I think about the cotangent, so cotangent is 1 over tangent. So cotangent then should have angles. I'm just trying to preserve some space. So tangent is opposite over adjacent. So cotangent is going to be adjacent over opposite. So if I think of this arc sine of x over 3 as an angle, the adjacent side then, so then I'm going to have the cotangent of the arc sine of x over 3. It's going to be, again, just the adjacent over the opposite. This is going to be the square root of 9 minus x squared over x. And now I can simplify my answer. So I'm going to find then, my final answer is going to be the integral of the square root of 9 minus x squared over x squared dx is negative so look back up here. I'm just filling this back out with with that first term simplified. It's going to be negative cotangent of arc sine of x over 3, which is right above this. It's that. So negative square root of 9 minus x squared over x minus arc sine x over 3 plus a constant. And that's my final answer. So again, you might be asking yourself, okay, why do I need to do all this? Why don't I just leave it as cotangent of the arc sine of x over 3? The reason is, dealing with those trig functions is much harder. Here I can look at this and I get a ton of information about what my solution is doing. This tells me absolutely nothing. I can't look at that and figure out what's going on. You wouldn't, if you were an engineer and working, you wouldn't hand this to your boss unless you wanted to be yelled at, I guess. But yeah, so we're going to do plenty more examples of that. It's all the same thing. We're going to just keep doing the same process over and over. We pick a substitution. We do the integral. We will then draw our triangle to figure out what, the cotangent of the arc sine or the sine of the arc cotangent of something is. But it's all going to follow that pattern. So I'm going to stop this video here. It's probably way over 10 minutes. This one took a while to do. But I'll post this as soon as possible.